Okay, then, so today we'll continue with sensor classification and characteristics. Okay, so let us start today's class. So what you see, you have seen so many types of sensor. You have seen position sensor, you have seen velocity sensor, acceleration sensor, force sensor. At least these four you are very much familiar with now. And each one of them can be of two broad classification, that is called contact type and non-contact type. So there can be a sensor which is based on internal sensors. These are internal sensors in case of robotics, basically may not be there in case of automation. It also can be an external sensor. Okay, but yes, internal sensors in case of robotics are position, velocity, acceleration and forces. These are something which is intrinsic to the working of the robot. That is why they are classified as internal sensor in case of robotics, whereas externally you have something called contact and non-contact type. Okay, so these are their position. You saw you have linear or rotary position sensors, and each one of them can be of incremental, absolute, potentiometer. LVDT is another broad classification of type of sensor. Okay, but yes, this is not commonly used in robotics joints, or not even in a prismatic joint it is there. Okay, so that is why I didn't cover this one, although resolver, synchronous are already there. Okay, in case of velocity sensor, all position sensors can be used, tachometer can be there, hall effect sensors are there. Yes, you already have gone through all of them. Acceleration sensors, all four sensors, namely you have already seen MEMS sensor, micro electromechanical system sensors, and force sensors you have already seen a strain gauge type of sensor. You also have piezoelectric sensors. If at all we'll get time, we'll come back to this and we'll cover this. You now know what is Hall effect switches. Okay, so that also is a type of sensor which is classified as force sensor. It can be converted to that form. Okay, otherwise it is normally used for proximity detection. Okay, and sometimes as a counter they are normally used, but yes, you know, each all can be interrelated. You can use position sensors as force sensor also. If you can have a position sensor, you know how much deflection can occur for a particular force in a element, then you can just check the displacement and you can estimate how much could be the force. So even position sensor can be used as a force sensor, provided you have those features put together in a form. Okay, so that is possible. And external sensors in robotics, these are external sensors. They are basically limit switches for the joint, pneumatic switches. It can be pneumatic switch, piezoelectric switches, pressure transducer, proximity, Hall effect. So these are some of the sensors. So that's all for classification. Now let us discuss what is different performance terminologies which are specific to sensors. What all parameters we should be concerned when we buy a sensor, or maybe when we have a sensor in hand, we want to know what all limitations does this one have. This sensors now includes sensors and a transducer, sensing element and a transducer together, we will call it as sensor now. So if it is a displacement sensor used as a force sensor, sensing element is the displacement sensor. Okay, although it is converted to the form which is called force sensor, and then you can have converter which converts it to a electrical signal maybe later. Okay, then that is what we mean by sensor here. So what exactly is a range? It is the limits and the span from where to where. Okay, this is basically the lower limit and the upper limit you can measure. Let us say you have a steel rule only. Okay, it has graduation from 0 to 15 centimeter, maybe a small scale you have. So what is the range? Okay, that is the limit. It is basically from 0 to 15, so it is 15 centimeter. It can be from 10 to 25, then also it is span is 15, lower limit is 10, upper limit is 25, but the span is again 15. Okay, so that is what is defined as range of a particular sensor. You have to take care what are the values that you want to measure. Your sensor should do that. Okay, error, that is the desired and the actual. So how much that difference maximum can occur, is that okay? Because higher is the precision of a particular sensor you go for, expensive it is. Okay, so more expensive it is. So it is not always possible to choose the best one which is there in the market. Okay, if it is optical sensor, it will be little expensive. If it is potentiometer, they are quite inexpensive. Okay, so but yes, different sensors has their own limitation in the term desired and actual. If it is 5 mm, that is the displacement I wanted to see, but actually it is showing the your sensor is showing something around 5.01 mm. If I am happy with this for my particular application, that is fine. If it is a gripper which is opening almost around 10 mm, I want to hold something which is almost a 1 centimeter wide. Okay, so it becomes very 10 mm wide and 10 mm of the object. You have to be very precise. Okay, so in that case, your displacement sensor of the gripper should be very much precise. But if at all your opening can go as much as 50 mm and object is just of 1 centimeter, you can be happy with that. Okay, so plus minus 1 centimeter is also okay. So yes, just if it is open, it is open. In case of gripper, normally it is like that. So that is what is error. Okay, accuracy, to extent to which a measured value might go wrong. So error is different, accuracy is different. Desired and actual, basically the difference is the error, but the extent to which measured value might go wrong. How much wrong? Can be positive, it can be negative also. It has nothing to do with what you exactly want to measure. It is just the accuracy, how closer you can be. Okay, so that is what is an extent, that is what is accuracy means. Yes, and then you have a sensitivity. Um as you know, you have a current sensor to say it wants to measure the current. You have a gain also. Let us say you have a operational amplifier that is checking the current flowing through a wire. Okay, so that is getting amplified and it is giving you some sense of voltage as an output. Okay, so it shows me the current flowing through this, and this is op amp which is sometimes multiplying by 5 times, 10 times, 15 times, whatever. So this is what is the sensitivity. Okay, so output voltage by the input value. So how much times it is getting multiplied, okay, how sensitive it is. If this is changing by a small amount, output gets changed by a huge amount. So this is called as a very sensitive. It is not just common to sensor, it is also common to actuator. Okay, it is common to many other things. Let us say you have a steering wheel, you have turned by 10 mm and your wheel actually turns by some 20 degree or 30 degree or so. Okay, so it depends how much time magnification is there. So that is what is dealt here. This is what is your sensitivity. These are some of the parameters to which you should be very much concerned of. Hysteresis and non-linearity. You see these two curves. Okay, these curves. Hysteresis is loading and unloading. Let us say you have a strain gauge element fitted onto a beam. You are loading it one by one. You want to check, yes, 1 kg, this is the displacement, 2 kg, this displacement. It is showing me something. Okay, so one gradually keep on increasing. It follows one curve. It follows the curve while loading. Okay, while coming back, it didn't follow the same curve, rather it has followed a different curve, whereas starting and ending points are the same. Okay, so this is what is the energy that was captured by the beam which is getting deformed, that is the energy which is required to deform and bring it back. Maybe it is wasted in the form of energy. This was very common while you were doing some magnetizing and demagnetizing curve. So this was there in case of magnetism. It is also there in case of any sensor. Can be a force sensor, it can be a displacement sensor, or a combination of sensor and transducer which is making it like this, and it can have multiple behaviors. Okay, so these three are the behavior which you see. One of them looks like just like a magnetic curve, so it is known as a hysteresis curve, whereas it can be something like this which is known as Smith trigger behavior. It can be a rubber band behavior also. So while loading it followed this, while unloading it followed this. So this doesn't look like a standard hysteresis curve. So all three are different. Your sensor can follow any one of them. And then there is something which is known as non-linearity. Okay, a line which is given by input and output, if it is related by y is equal to mx plus c, is it linear? Is it linear? No, this is not linear. It is defined as, if at all you multiply the input by a factor, okay, the output gets multiplied by the same factor. Okay, so that is what is linearity. Okay, so till here it is linear, but this makes it non-linear. Or you can have y is equal to k sine theta. Sine theta. Theta is the input, y is the output. This is highly non-linear. You see, this is sine A of that. So multiplying theta by some value, if at all it is a displacement sensor, angular displacement sensor. So multiplying this by any value k will not make k times of y. So this is again non-linear. So anything that behaves in this manner are non-linear. Okay. And why we prefer having something which is very linear? It is easy to understand, depict, calibrate and use it. Okay. So that is the reason we want everything to be linear. In real world nothing is linear. So what happens? You have linearizing circuits which are placed inside the transducer part of the sensor. Okay, you convert a type of signal to another type and then you try to linearize it so that output is, let us say you have a accelerometer. Okay, it is changing from 0 to 1G, let us say. Okay, and then output voltage changes from 0 to 5 volt. So if at all it can be linearly interpolated, input and output can be linear related, it is very easy to understand. So as soon as you get 2.5 volt, you know it is G by 2 which is there, is it not? So that is why it is very easy to understand. So that is what is linearity and non-linearity also. So reproducibility or repeatability, it is ability to give the same output for repeated application of same input. That means again, if you know the bullseye like this, okay, so you want to hit here, okay, your sensor is giving, you want to measure this, but for this value, this particular value, your sensor is giving this value. Okay, next time this value, this value, this value, you are getting all the values nearby to this. Okay, all the values which are nearby to this. So it is repeatable. Every time you know how much maximum deviation that can occur. Okay, so if you know that, it is fine. In robotics this works very well. Okay, so you always say your system is so much repeatable. So best is the, if you are getting a value over here and rest of the values very nearby, this is very repeatable. That means you precisely know, yes, this is the error that I am going to see if I want to measure this. I want to go here, but I always go here. I know this much of error is going to be there, so I should be happy with that. Okay, this, because in robotics what happens, you teach and repeat. Okay, so if you have taught for a point and robot is able to go to that particular point irrespective of whether you wanted to go to a particular coordinate, It is going there or not doesn't matter, but it is going first time every time. Okay, you have taught it the first time, every time it is going there. You should be very happy. So that is why in case of robotics, repeatability is most important. Okay, so this is one thing, that is what is meant by it is the radii of the circle maximum, smallest is the radii of the circle from that particular point where you are going every time, so better it is. Okay, ability to give the same output for a repeated application of the same input. So that is what, and then you also have stability, ability to remain there, okay, to give same output for a constant input over a period of time. You have commanded to go to a particular place, it should remain there, it should not drift. Okay, with a change in temperature, yes, you can see some sort of drift. It can be an actuator which is behaving like that, it can be a sensor which is giving you a drifted value also. Okay, it gives you 5-volt reading for a 3-volt. Okay, 5-volt was quite good enough, but it should not drift 5 plus minus 1 volt. It is deviating from that, so it is bad. As long as it is to a particular error, it is fine if it is repeatable, but yes, it should not drift from that too much. Okay, so that is, it should be stable, and that is caused mostly due to the change in temperature. Okay, or maybe over a period of time, the if it is hanging for a long amount of time, yes, you may see some sort of creep which is happening. So these are some of the reasons why they happen. And then you also have something which is known as a dead band. What is dead band? That is the backlash. As in case of a gear, what you see, this is the distance which is there. If you change the direction, your gear was rotating like this and your wheel was following that this way. This is the constant point of contact, so it was constantly moving. As soon as you change the direction, as soon as you change the direction, what will happen? You want to go this side, it's going to go this side. So this particular gap is going to create that delay. Okay, it won't change the direction immediately, rather it will stay idle till this surface, the surface which is this, comes in contact to this. So as long as this doesn't come in contact, no motion is going to be transferred from the input shaft to the output shaft, is it not? So this is what is a backlash, and that is there in case of gear. In case of sensors, we call it dead band. It is not going to respond for a range of input, and there is no change in the output. So that is what is dead band. Then you also have resolution. Resolution, what is that? It is the least count, the smallest change in the input that will produce an observable change in the output. That is the smallest change. Until unless you change by a certain value, output is not going to change, or the least value your equipment can measure it. In digital thing, it is very important. Let us say you have a sensor that gives you an output in terms of 0 to 5 volt, but I am transferring it digitally using a digital analog to digital converter, ADC, to a microcontroller. Okay, so if it is a 4-bit controller, so how many values intermediate you can see? 0 0 0 0 to 1 1 1 1, that means 0 to 15. Okay, 2 to the power 4, that is total 16 values you will see. That means intermediate 15 different points you can see. Okay, so it can be 0, it can be 5. Intermediate values what you see are not analog, rather you see some discrete values, and those are intermediate 15 different values you will see, that varies from 0 to 5. Okay, so you won't see all the values. So that is digital, and this is the gap which is there, and that is the resolution. In case of analog to digital converter, it can have 4-bit, it can have 16-bit, it can have 32-bit and more. Okay, it all depends how much precise you can be, what should be the least count. what is the resolution? It depends entirely on the resolution of your equipment. In case of any digital device, it directly the number of bits of conversion that is happening. Okay. So that is why it is very, very important in case of this. Okay then, so coming to next, you also have output impedance. Why this is important? Because you have to connect your device which is taking the value. Let us say you have a sensor which has a transducer, it has its own impedance. That why it is impedance, it is not just resistance, because it is not purely a resistive circuit, rather it has many other things which are associated to that. Finally, it is not purely resistive in nature, it is impedance. Okay. So, and more so, it is the signals are not pure DC in any way. Okay, it is a varying signal. So we are more concerned of the impedance, not of resistance. If it is a DC, we should be happy with resistance. But as because it is just like a AC, it is varying. So you should require, you need what? You need to know the impedance of your system. Now, let us say this is your device. Okay. Okay, it is to be fitted to a computer, it goes to a PC. Okay, and it has its 8 ohms resistance to say. Okay, your PC also has got some internal resistance which is here. As soon as you connect it to your PC, there is some drop in the voltage, there is some drop in this voltage. Why? Because in parallel, if this PC also has got 8 ohms, although it is not, this is just an example, if this equipment was 8 ohms, this also was 8 ohms, in parallel now it is 4 ohms, both are in parallel, so it is 4 ohms now. So there will be significant drop in this voltage. With 8 ohms, if this is 5 volt, so with 4 ohms, that voltage will be dropped, because now it will carry more amount of current through this circuit. Okay, so that can be one of the reason if it is supplied from external source. Okay, so that is why normally we prefer to have a very high impedance if any equipment is fitted in parallel. Probably you have gone through this when you were using a voltmeter, a shunt. If you want to apply to a voltmeter, so you preferred what? To voltmeter should have a very high resistance, so that any attachment, any shunt attachment should not affect the drop in the voltage across the voltmeter. So that was one of the reason that you saw. Same is the reason here, that you need to know the impedance, because you have to take input to your PC or sometimes to the microcontroller. You should not be bothered, nowadays they are designed with such that yes, you can use it. Okay, so we'll see one of the data sheet what impedances normally they provide. Okay, we'll see some examples data sheet also today. So this is why it is important. So any equipment, if it is to be connected, let us say if you have a speaker and that is an output speaker, so it basically defines how much current it is going to take away from your system. Your USB, if it is supplying to a sensor and your sensor is of very low impedance, it will draw a lot of current from your USB, and then your PC may cease to work properly, right? So your sensor should not draw too much amount of current. So that is why a high input impedance is required in these type of sensors, which are supplied by the PC power itself. PC is a good example, because most of the days nowadays we use PC as an interface, okay, or a microcontroller also. So okay, then comes a bandwidth, that is the maximum operating speed or the frequency. That is what the bandwidth. It is not the band, it is not the range that you saw earlier in the first serial number 1 of this today. Rather, this is the bandwidth. It is how frequently you can change the input and your system keeps on responding. Your output also responds to that frequency. So that frequency is called bandwidth. Okay. So if it is a transistor, your switching should not be very fast. If it is very fast after certain frequency, It will directly give you 1 or directly give you 0 all the time. It won't change along with the input change. That is one example. That is the reason you switch to UJT or some MOSFET switches. Okay, so that was the reason, and same is the reason here. Your sensor, if it has to check some proximity, as I have said, so proximity, what frequency it can check, okay, how fast that conveyor can move with an object lying on top of it, and you can still count the number of objects that has passed on that conveyor. That defines the frequency. So for a capacitive proximity switch, it has some value, some frequency it must be having. We'll see what it is. Okay, so that is why this is just an example that a counter which can be a proximity sensor that just counts the number of pellets which is moving on a conveyor. Okay, so that is why frequency is important. Okay, output type and the interference. Now your sensor can give you voltage as an output. Voltage as an output, that means for some displacement it is giving you, let us say, 5 volt, and for some other displacement it is okay. So that is the voltage corresponding to a particular displacement. It can be current also. Higher, what type of devices are they? Higher is the input that is there, higher is the current this will allow to flow through that particular channel. Let us say you have a system which is like a gate. Okay, so and this is where your device is sensing and this is grounded. So if this is the input to the from the sensor which is coming, so higher is the input. This is a voltage which is coming here. If it is in a transistor mode, okay, so higher is the input, higher is the current that flows from here to here. So what it is effectively doing, it is converting this voltage to a current signal which may be proportional, not always though, to some distance, to some range it is proportional. So this current flowing through this, due to this source, this current is proportional to this voltage. This is just a example, okay. So what it is, what I meant here, your output can be directly this voltage, and you have analog to digital converter, and this digital value can get into a PC. That is fine. Okay, your sensor is giving you an analog voltage, convert to a DC, analog to digital converter, digital, and PC takes it. That is fine. Sometimes these type of conversions are also there within the sensor, and what you have a current which is given as an output. Your inside of the sensor is something like this, and as an output you don't get this voltage, rather you get this current, and current is proportional to the sensing input. Okay, it can be a temperature, it can be something else. Okay, let me clean it off and I'll show you how such thing can also be converted to a voltage signal and finally converted to analog to DC and digital and used. Let us say you have a sensor that is giving you a current value which is proportional to the sense. Okay, sense can be anything, it can be temperature. You just fit a resistance, a high value resistance here, and what you can do, you can measure a voltage from this end. Okay, so this current, this is a fixed resistance, so voltage across this resistance will be proportional to this current, is it not? So voltage is proportional to the current flowing through this resistance. Now this current signal is converted to a voltage signal, and again this voltage can be converted to analog to digital converter and can be fed to a PC. Got it? Or a microcontroller. So this is how different conversions are done, and you should know what type of sensor you have got in hand. Okay, so that is why this is very, very important. Your sensor can be a voltage, it can give you a voltage signal or a current signal. Normally they are electrical in nature, that is why I confine my explanation mostly to electrical things only, that is voltage or a current one. But yes, it can be a mechanical output, it can be some optical output as in case of encoders, what you got? You got the count of light signals corresponding to the number of windows that has passed, as in case of optical displacement sensors. But again, you converted it to some electrical signal through by attaching an LED and a light sensor. Can be a level, it can be pressure. All these can be easily converted to electrical equivalent. Okay, so we work on this region most of the time. Okay, going to next. Okay, then your sensor, if you buy a sensor, it tells you within what operating range. It gives you a value which is quite within the definition. If it says it has this much of repeatability, or if this is the resolution, that is true within the given environmental condition which is defined by the manufacturer. Let us say if it is working temperature, it varies from 0 to 70 degrees centigrade in case of industrial sensors. If it is sensing acceleration, then also you should know that acceleration or the voltage corresponding to the acceleration, that is valid only if the sensor itself is lying at this working temperature. Temperature is just an example. It can be pressure, it can be vibration also. Your equipment cannot handle more than this vibration, otherwise your accelerometer will give you a fake reading. Got it? So these are some of the performance parameters which are very much in use. Others can be the size of a sensor, which is very important, is it not? If you have to fit it compactly within a sensor which is here, maybe my sports watch or anything like your mobile phone, so that size is that footprint of the sensor is very important. Weight also matters a lot, because you are into designing a product, you should be worried about the weight. Like as gave you an earlier example, when a gyroscope could be as huge as a 5 kg weight, it's a big one, which were earlier days they used to carry on a fighter airplane. Nowadays with a MEM sensor, they just remove it and they can carry more ammunition nowadays. Okay, how much reliable it is, how many cycles it can operate. If you are buying a limit switch, it says 1 million cycle. Not just a limit switch, even your keyboard in your computer, it says after so many years you have to throw it off, because one of the switch q, if you press it 5 number of times, you see just one q appearing in your screen. Why? That switch has gone bad. So many million number of cycles have finished. Gamers should be worried of that, how many times your keyboard can take up. Okay, not valid for touch switch most of the time. Maintainability, what could be the cost if you just replace this sensor? What will be the replacing cost? So for design engineers, these are something which are very important. Now let us see static and dynamic characteristics, that is the impulse response of a system. This is more towards the control aspect, but yes, this particular curve you will find many places. How your actuator is behaving, how your sensor responds to a particular impulse input. So this is exactly the same curve, or maybe your dashpot, a dashpot which is a spring and displacement. If you have, you must be very familiar with this curve probably. If you just leave it, you just give a impulse force to a spring mass system, it simply displaces to a certain value, it oscillates and simply comes to a stable position. This is exactly the thing. In case of sensor also, it is a similar thing. You have given some value, let us say it is a voltage sensor. Initially your output was 0 because input was also 0. Now you have all on a sudden put 1 volt to the input, and how the output should show you. Output immediately it won't show a value corresponding to 1 volt, rather it will go to some value more than 1 volt. Okay, it rises to a value. Okay, and then 1.1 volt it comes back 0.99, and again it's a steady state. At infinite amount of time it will take, almost it will give you 1 volt for 1 volt as an input. Okay, so these curves should be very compact and small as so we'll see what all parameters which are there for such a behavior. Okay, so first of all, first thing, dead time. Your sensor didn't responded only. So and until unless it has rose to a particular gap. Okay, let us say you have put some value as an input, your output is changing. You put this as an input and immediately it didn't responded for quite number of time. Okay, so this is the dead time, it didn't responded. Then again it rose to a 5% of the actual commanded value. Till here you call it as some maybe rise time or something like that. Okay, so this is a small amount of time from where it rises from this value to certain distance, that is 95% of the commanded value you have reached. So this is what is the rise time. Then you have overshooted to a value. Okay, this is the peak that you are going to see, and again it comes back. So you see there are many things, but few things which are very important, that is this settling time. After this settling time, the value you get, it is not more than this much of a error, 2 to 5% within the commanded value, and I am happy with that. Okay, and that is the time which is known as the settling time. And for electrical sensors, these times are very small. Okay, you won't even come to know it has responded. But for mechanical sensors, it takes some time. Okay, it takes some time, and this is the peak value. How much maximum should I see? Okay, but in actuator it is very dangerous at times. I commanded to go to a certain place, it has overshooted. Okay, if it has to pass through just near to my nose, it will bang my nose. Okay, so that should not happen. In case of actuators, they are very much disastrous. In case of sensors also it can be, because with this sensor you are controlling your actuator. So this sensor should also be so responsive and so best. Okay, so that is the reason we are concerned about, and this is the transient deviation. So we'll just see what else. So this is how a curve look like. Let us go to these. Okay, response time expressed as a percentage of input. Okay, so you see this was the response time. Okay, I'll erase them all so that you can see clearly when we come back to this. Yes. Okay, so this was expressed as percentage of the input. Time constant, it is 63.21% of the response time. Okay, this particular value, I think quite a lot of you know already. Where from this? Why 63? Why not 62? Okay, this is actually a factor which is very popular in sometimes in half-life, in radioactivity, and many other places you must have seen. It is exactly this value, 1 minus 1 by e times. If it is a logarithmic decrement, you come across this. So it is exactly this value that comes, and that is why it is known as a response time. It is the this value, till this value, this time is known as the time constant. Okay, till your sensor reaches this value. So that much time is called the time constant. And then what is next? Rise time, specified as a percentage of the steady state till 95%. The time taken to rise till 95% of the actual value is the rise time. Again, it is specified as percentage of the steady state. Settling time, hope you know this already very well. Output settles within percentage of the steady state. Example, 2% of the steady state value, what it is to give. Okay, so that much time is the settling time, and remaining I'll show on the data sheet now. I hope till here all the parameters are quite clear. I'll just open a few of the data sheet and I'll discuss them. Okay, so let me go to one of the sensor, which is ADXL 345. What it is? This is a digital accelerometer. What it can do? It can measure the acceleration, 3-axis acceleration. You see, it is not just one axis. It can detect axis 3 different acceleration in 3 different Cartesian directions. Okay. So, and it can go up to plus minus 2g, plus minus 4g, plus minus 8g, plus minus 16g, depending on different packaging of this, or maybe different configuration which are set inside through digital means. Okay, you can be in one of them. Okay, if you are using just accelerometer which are fitted in your sports watch, this should be quite good enough. Okay, but if it is in a collision detector, even this may be less. Okay, at 16G. So you can put your accelerometer to different configuration. Okay, so one of them is always active in a particular. Once that configuration is set, it starts working. So let us see what all parameters which are here. It says it is of ultra low power device. It is of analog devices, ultra low power device. So it carries how much current when it is active? 23 microamps. You see why these batteries they last so long. If it is a sports watch, once you charge it, it can last as long as 15 days. A Fitbit band was released with no battery charging thing. Okay, and once you charge it, it lasted something around 1 year, and you just have to throw it off. You cannot recharge it. Okay, so such a bands are there. Why? A single battery which was placed here and packaged in a sealed thing. You can go inside water any deep you want, no water ingress will be there, and you need not to do any charging, because if they provide any charging hole or something arrangement like that, so IP will be affected. So that was the arrangement there. So this is 23 microamps, you see, and typically 2.5 volt it works on. So, and in standby mode it is 0.1 microamps. So you see, if you are running, okay, 23 microamp it will draw, but if you are stable for a particular period of time, it takes just zero point 0.1 microamp. So it is quite good. That means during night time when you are not running, it can go very long. So if you use it, it is consuming, otherwise it is not consuming. So that is why it comes under a ultra low power device. So now you know where to select the device. Power, these devices are very power hungry. Okay, so you have to be very choosy on this. Okay, power consumption scales automatically with the bandwidth. Okay, so it is scaling with the bandwidth. That means, that is what I said, higher is the frequency of input, higher is the power consumption, otherwise it is very less. User selectable resolution, it is fixed to 10 bit of resolution. 10 bit means 2 to the power 10 subdivision of, if it is in a one of the mode, let us say if it is in a 2G mode. So 0 to 2G, okay, it will have 10 bit of resolution. That means 2 to the power 10 intermediate acceleration values it can give you. That is quite high. And full resolution with a G range can go as high as to 13 bit of resolution at 16G. At 16G, if you are using, it has 13 bit of resolution. That means it is very precise equipment. So many small and lower significant bit. LSB error is there. LSB error, that means, what is LSB error? I should tell you. Let us say you have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is which one is LSB? LSB and MSB. If you change this, you will see a huge amount of change in the value. If this is changing, you won't see much of a change. Okay. So if it says it is last 2 bit LSB, it can keep fluctuating. 2 bit of error in LSB in case of 8 bit of system will not change the value much. Okay, last 2 bit can be erroneous. Okay, so that is what is specified here in case of this 4 mg of LSB, milli G, 4 milli G of LSB is error is there. Milli of G value it is saying, it has converted that bit to the G value, how much G error you can see based on that particular LSB error. So this is what is there. Okay, and then you see free fall detection is there. If at all your device is falling from a certain height, it directly detects, yes, you are moving at a 1G, and it immediately can tell you there is a trigger which tells you, yes, now your device is falling. Okay, and you can immediately detect. Let us say if you have a hard disk, you want your uh, hard disk head to park as soon as your device is falling. This is the way you can use it. Okay, so it has a free fall detection, so many features. Input and output voltage range is 1.7 volt, that is the input voltage which is required to Vs. How much was Vs? That is typically 2.5 volt. You see, so it runs on a lithium ion cell quite easily. Okay, it can run on a lithium ion cell very easily, and it has SPI for communication, serial peripheral interface. SPI is there in your microcontroller. It also has I2C, that is twin wire interface, Philips proprietary way of doing it. So I2C communication, that is normally there in microcontrollers. SPI is also there. You try to learn these are there in Arduino boards. Okay, so with these two ways you can take the data out from this particular accelerometer. So these are ways of communication. That is why it is not giving you an analog value. Rather, it is already doing everything within the chip and giving you a digital value transmitted through these modes, SPI. In case of industrial sensor, it can be EtherCAT and Profibus, Profinet, Ethernet. Those ways of communication are used because they are for a longer distance. For onboard communication and small devices, these are the ways it is communicated. Okay, and then SOC signal, although it can measure just up to 16G maximum, it can take this much of SOC. 10,000 G of SOC survival. That means even after collision, it is not going to go back. 10,000 G is huge use of a G value. Even satellites, they don't go to that value, rockets, nothing. So these are so safe, and it is LGA packaged array of this much of footprint size. They are very, very thin, 3 mm by 5 mm size and 1 mm in thickness. LGA package, grid array package. Okay, I think I am not sure, I will have to see the packaging information. It is basically a grid array. It is they don't protrude out their pins like a standard chips. Uses, you see, it is used in handsets, medical instrumentation, gaming and pointing devices, industrial instrumentation. Also, you just have to convert the way it is communicating, right? Personal navigation devices, hard disk protection, as I have said. Okay, and this is how the internal circuit looks like. Okay, so what all things? It has a sensing element, it has conditioning electronics, analog to digital converter, filter, and then communicating in it. This is what is converting it to serial communication mode. Okay, these are the interrupts which may be high for trigger mechanism. Okay, trigger mechanism for free fall detection. So these are maybe interrupts which is high only when in that particular condition. This is chip select. If this is high, then only this chip will work. This is ground. This is voltage supply. VDD is the ground, and this is the chip serial number. AD stands for analog devices. Okay, so yes, and then there are many other information. This is what you should be very much concerned of. Electrical guys can go further deeper into it. What is the electrical impedance? Those things are also here. See, this is the resolution. So further details are there. Sensitivity, input and output, gauge sensitivity is also given. Offset. Offset is also given. Noise level, how much could be the noise it is given. So there are many other things. Maybe if you are designer, you should be worried of how much power it is taking. Self test is there also. As soon as it starts, it does its self test. If it fails the self test, it gives you some trigger. Okay, so you know your device has gone wrong. Okay, so weight, yes, temperature, this is the environmental condition. It works from -40 to 85 degrees. So even on the poles, maybe it works. Okay, even at 85 degree for, so it is very well suited for industrial environment. There are many other things, how to communicate with device. Okay, how, what all pins which are there. Okay, performance characteristics, so many other characteristics which are there for designers. Okay, if I see something very important relevant to you, I will stop. So this is SPI communication, how that is to be done through a microprocessor or a controller. What all wires which are of importance. Okay, this is how they are connected, how to select a chip and take the data out. There are electrical characteristics also, but nowadays these are prefed to a PC or a microcontroller. You don't go things to that scratch, they are for designer now. This is how that wires are to be connected. There are some default resistances which are there. That's all I think, yes. Okay, let us go to some other sensor now. I don't see anything. Maybe packaging information. These are the memory map, how, where these values are stored, where from you have to take the values. It is not that difficult, yes, although datasheet looks quite complex, but actually it is not. You get ready-made APIs to handle these registers, and yes, you can design your own circuit. I, being a mechanical engineering student long back, I have been doing it since long time now. So you definitely, you all can also do. Okay, so that's all this one. Let us go to some other sensor. I'll close this one. Okay, this is what is a low cost 4-stalk sensor. Low cost 4-stalk sensor. Okay, what all things which are here? It communicates by Ethernet, EtherCAT or RS485. That means you see SPI, 2WI, I2C, it is not there. It is purely an industrial way of communication. Supply volt 12 to 20, 30. Again you see it is not under TTL level or a MOSFET or a CMOS level. Okay, so it is above, so it is purely industrial device. Resolution is 16-bit. Now you see in industry they are not happy with 10, 12 or 15 bits. Okay, so it has gone as high as 16-bit. More precision is there. Sampling rate, that is 8 kilohertz sampling. Basically it is very much similar to your bandwidth, how frequently you can change the forces and it will still detect individually each one of them. Okay, the operating temperature is not very good, it is 0 to 65, it cannot go to poles. Ingress, yes, it is IP64. Dust and splashing water, it is okay. Okay, and then what are the ranges for different makes of it, different models? FXY, okay, and then you have FZ, X and Y, it can sense up to 150 Newton, FZ can go, Z is more, that is 470 Newton. The way it is constructed, you will see in my slide, you will find why it is in Z direction, it is more. And then it can detect torque along 3 axes, maximum to 8 Newton meter. So it doesn't provide you much of data, because industry, things are very much already secured. You don't go by design, you normally are the end user. High accuracy, 2% of full scale error, it is accurate. Signal to noise ratio, it doesn't provide much of a data. It directly provides how to use it, how to fit this with an adapter plate. This is the sensor, your robot, this is the adapter plate. And then after this 4 sensor, there is another adapter plate which can fit a gripper. So it comes sandwiched in between your robot end effector and the gripper. It comes in between, somewhere in the wrist. Okay, so these are the flange drawings, how you can use it. Okay, so this is your force torque sensor. I'll just see if I have any other type of sensor. No, I think that's all. You got the idea mostly what type of sensors and how many ways they can specify these sensors. Hope that is quite good enough for today's class. That's all for sensors. Thanks a lot.